this is what it would look like if you equalized number one, so if you equalized it, this is what it would look like. That's equal, sorry. So that's, sorry, E minus RT or NF, and so that you'll have to draw a bracket here, and then R, RT over FZ, ln X over I, that's that. Now you'd realize, okay, so we can now calculate this, and we could, if we had this, then we'd be able to calculate this or this, and you know, and that way we would be able to calculate quite a lot by using equipotential you know, equalization. So that's how things are. It's not very difficult at all. If you read Biophysics, it'll help you out quite a lot. There's a very important good book on biophysics that you'll find useful. Let me just bring it. Now, if you read this in this particular book, the Rodney Coterill in Biophysics, an Introduction by Wiley, you'll come across this equation on page number. See, on page number it comes talks to you about PV equals nRT, the one we discussed earlier, and then yeah, this one. So this is, we're getting close to the voltage calculation, which is volts per meter. The Nernst Goldberg is quite similar, and then you got the so in this particular book you'll find all the actual analyses that you need, all the equations that you need to calculate electrophysiological calculations. So Nernst would be somewhere (242), page number 242. Now the Nernst equation, it says here, it's this kind of system, and it's to do with calcium, sodium, potassium, and magnesium ions, and you have to understand the resting potential, the firing potential. You have to understand polarization, depolarization, and yeah, so I'm very difficult to hold it in one hand. Now let's recap what we've just discussed. So I started off from here, and it was chemical kinetics, Gibbs free energy, a bit too, you know, straightforward. And then I told you about, you know, this equation. It contains RT, and then the Q is from this equation, the arrow sign. And it's all about thermodynamics, the adiabatic, isothermal, isochoric, isobaric changes, and the Gibbs free energy is a calculational facility to carry out entropy change and entropy changes in the system. Now, what the common factor between these equations and the Gibbs free energy is the RT log natural thermal energy. So that's why I mentioned this, and that's because it's the least discussed equation in advanced chemistry. Then I use this equation to bring it over to this page, and that's where I told you about the K constants, Arrhenius equation, factors, the collision theory, bounding motion, and the rate equations, the two different forms of rate equations and how they can be reconciled, as well as how you could take the rate equation and equate it to Arhenius equation and make your life easier. And so I gave you a few examples here of partial pressure, or how to put the equilibrium, how to put the products and reactants on top of each other in an equilibrium equation. And then the last but not the least, we came onto the center part, the Nernst Goldberg system, which has two different facets, and I discussed the first facet and the second facet, and I told you about its importance of calculational analysis and diagnostic approach in cellular electrophysiology and cellular transport kinetics. And I spoke about Fick's law, which is quite mechanical, quite crude, to do with the thickness and length of the membrane, and discusses proportionality of concentrations, down the concentration of solutes and solvents, down the concentration gradient. And we discussed pi equals CRT, and I told you how it was similar to P equals CRT. And then I talked about active transport, facilitated diffusion, passive diffusion, osmosis, and reverse osmosis. And I also finally equated this for you, equated this, and into this. And that's a bracket. Bear with me, please. I'm missing a bracket here. Sorry, that should have been a circular bracket, and I've put double brackets because I've put double brackets because you calculate the dividend, natural log, press natural log in calculator, then multiply it by RT divided by F times Z. So either you divide them first, take the natural log, write it down. You write down R times T, write it on top, then divided by F times Z, 96,500 times oxidation number, write it down, and then you divide these two in the calculator again and multiply it with this, what you've got here, and that's when you'll get the correct answer. If you this is slightly complex for calculator agility. It forces you to become an Olympian of your calculator. If you don't do a good job and don't follow the sequential synchronicity, you may and you will miss out on a correct answer, and you'll only get marks till a little bit above till before you were able to calculate the correct answer, which I mean is that you won't get the marks for a correct answer, which is majority of the marks, and you'll get like 3 out of 5 or 2 out of 5. You won't get 5 out of 5. So you have to take this concentration, moles per dm cubed, divided this by moles per dm cubed. You get a ratio. You log natural that ratio, press shift log, and then you do it. Then you multiply it times, so you multiply times T times R, and divide it by F times Z. And you have to do the same here. It's a lot simpler, and that's the electrode potential. The electrode potential of the ion in question. So again, please take a screenshot. And 5, 4, 3, 2, 1. 5, 4, 3, 2, 1. Please crop it. And 5, 4, 3, 2, 1. And you may crop it now. So I'm going to entitle this video Synoptic Analysis of Chemical Kinetics, and that way you'd be able to understand where I'm coming from. My next video will be about radiopharmaceutical transport kinetics, where we'll discuss different types of radioisotopes and their use in nuclear chemistry. Thank you very much for watching the video. I hope you learned something today, and I'll take it from here. Cheers. Take care. Bye now. If you've got any comments, please post them down below, and I'll try to answer them. Thank you.